Hello, AP Calculus students. Welcome to This Week in AP Calculus. This is Mr. Rich. I am going to this week show you how to use the idea of limits to define and check for continuity of a function at a particular x value. So that's going to be the topic tonight. Is we're really going to take a look at how these limits that we've looked at the past few weeks, how they're used to define when a function is continuous or when it is not continuous. And if we have time tonight, my plan is to also show you the intermediate value theorem, which is also using limits. So hold on just a second. I'm going to put my dog outside. If you are watching on the live stream or if you are watching on the replay, be sure to put down in the comment section where you're from, where you're watching. I'm in Jacksonville, Florida, and I've got quite a few students here taking AP Calculus with me. We're about to start our third week of class, and we've got just a few more topics to cover in our class, and we'll be ready for our first unit test, which is going to be next week, and we'll be covering limits on that unit test. So I'm going to share my screen here. We're going to get right into the idea of continuity and how we use limits to define and check for continuity of a function. Okay, so give me a second. I'm going to share my screen. Okay, very good. So here's what I want to do to start off. I want to take a look at some functions that are not continuous at a particular x value. And what I want us to do is to look at each one and determine what is the function at that particular value of x, and then what would the limit be at that x value. So here we have a removable discontinuity on this first function. And if we were to ask the question, what is f of 1? We would see that there is no y value, so we would give it a DNE. So the function does not exist at 1. Now, I could ask, does the limit exist, right? So as we approach 1 of our function f of x, which implies, of course, we're looking at both the left hand and the right hand of 1, we do see that that function converges on the number 1. And so we would say that although the function doesn't exist at 1, the limit does exist, and that limit is the number 1. Let's look at that same function, though, but with a dot right there. Again, asking the same question, does the function exist at 1? And in this case, it does, because we can see that there is a y value of 2. And if we still, though, ask for the limit of the function as we approach 1, that limit is still 1. So for the fact that the function did or didn't exist at 1 really didn't affect the limit. The limit was still going to be 1, because the limit's not talking about y values exactly at 1. It's talking about as we get close to 1 on either side. And so we have that situation. Let's go here to a jump discontinuity. Here we can say that, well, let's first ask the question, does the function exist at 1 in this case? And since these are both open circles, there is no y value when x is equal to 1. So that is definitely a DNE. Now, what about the limit as x approaches 1? Well, we would have to say that that doesn't exist either. And we know that because of the limit existence theorem, which says that a limit, which implies a two-sided limit, right, as x approaches a single value, that limit's only going to exist when the right-hand limit and the left-hand limit are the same value, and that value is a real number. And in this case, we can see that the right-hand limit is 1, the left-hand limit is 3. Therefore, the limit overall as x goes to 1 does not exist. All right, so let's go to the next one. In this case, we do have a value. Our discontinuity here is at -1, but our function at -1 does exist, and it's 1, but the limit as we approach -1 would not exist. And that, again, similar to the previous problem, is the right-hand and left-hand limits are not the same value. The left-hand limit is 2, right-hand limit is 1. Here we have an infinite discontinuity, which is at 0. So there is a vertical asymptote at x equals 0, so the function does not exist. And then if we try to take the limit as x approaches 0 of our function, that limit's not going to exist either, because, well, for a limit to exist, it has to be a real number. And from the right, it's going to infinity. From the left, going to negative infinity. So that limit's not going to exist. Now, in each one of these cases that we've just looked at, we have a different combination of whether the function exists or not, and whether the limit exists or not. In this case, function doesn't, but the limit does. Okay. In this case, they both do exist, but they're not the same value. In this case, neither the function exists nor does the limit exist at that x value. And here's a case where the limit doesn't exist, but the function does exist at -1. And so I don't know if you see the pattern of what's going on here, but this does allow us to come up to with a general conclusion about the relationship between the function at a particular x value and the limit at that x value. And I'm going to state it. Oh, and here's a case where neither one of them existed. Okay, so let's formalize what we see in these examples, and then maybe we'll come back and take another look at those graphs. So I want to give you the limit definition of continuity. So a function f of x will be continuous at x equals c if the following 3 conditions are met. And the very first condition is that the function evaluated exactly at c must exist. So that's one thing for sure. If the function does not exist at that x value under consideration, then how could it really be continuous there? All right. So we saw several examples where the function doesn't even exist at the x value. So game over, it's not continuous if the function doesn't exist there. The second requirement is the limit as you approach c for that function, it must also exist. Now, we did have one case that we looked at where both the function existed and the limit existed, but it didn't meet the third criteria, and here's the third one. If they both exist, they both have to be equal to the same value. All right, so this is the third requirement. That value, f of c, it's going to have to be equal to the limit as x approaches c of f of x. And you'll see for all of those graphs that we just looked at all of those graphs, none of all 3 of those conditions were not met. So if we go back and we look at this and maybe check each one of these graphs for these 3 conditions, you'll see that this this thing actually does work. The first one here, well, the first condition was the function must exist. Well, function does not exist right here. And so it doesn't exist, but the limit does exist. Now, this is a removable discontinuity. And if we fill in, right, if we fill that in, fill that dot in, then all of a sudden the function does exist, and it would be 1. And since they are the same, it's continuous. All right, let's go down to the next one. Well, the first condition's met. The function does exist at x equals 1, and that is 2. And the limit does exist, but they're not the same value. So this fails, right? This fails condition number 3. So it is not continuous. And this one failed right off the bat, right? So this failed condition 1. If we go to the third one and take a look at this, this fails again, condition number one. So this fails number one. So definitely not continuous. This doesn't fail one, but it does fail number two because the limit doesn't exist. All right. So this fails condition number two that we had looked at. And then we look at this one, fails both conditions one and two. So it's definitely not continuous. Now, you might look at that and go, Rich, why do you, excuse me, clear my throat. You may say, Rich, why do we have to have these three conditions and consider them when I'm looking at the graph? That's a fair question. What's up with that? Just look at the graph. Well, the point is that we're going to be working with functions. We don't have a graph. We'll be looking at just the function itself, and then we have to apply those three tests to see through analytical means without the benefit of a graph whether the function is continuous at a particular x value. So that's what we're going to be doing here. So there's our three conditions, and let's work some example problems. So here we have a piecewise function, and it's saying here, determine if g of x is continuous at the given x value. So we want to see if the function is continuous at x equals -3. So what we'll do is we'll first see, number one, what is g of -3 and see if that exists. Well, if I'm evaluating exactly at x equals -3, I would be using that function right there, and the answer is 5. So the function does exist. Okay, now, what about number two? Number two, we want to see what the limit is of my g of x function, though, as x approaches -3. Now, that means then that I would not be using 5 because a limit, as we have said over the last few weeks, right, the limit is really only just telling us what's happening to the left or the right of that x value. And so that means I would have to be using this function just to the left or right of -3. But there's a problem. I can see that this function has a vertical asymptote at x equals -3. Or actually, shouldn't say that, right? It has a hole. So let's take a look at the g of x function. So what I'm going to do is this. I'm going to go ahead and write this in its factored form. So I'm going to factor the numerator as the difference of two squares, and my denominator is x plus 3. So what happens is that that's going to cancel. So I have a hole on this function at x equals -3. All right, so what I'm going to do is I'm going to take the limit then as x approaches -3 by direct substitution, and the limit does exist. And that limit is -3 minus 3. It's a -6. So the limit does exist. Right? The limit does exist. But the problem is that g of -3 is not equal to the limit as x approaches -3 of g of x. So I can say that g of x is not continuous at x equals -3 because it does fail condition number 3. So, what is happening? If you wanted to take a look at what this function would look like if we graphed it right around 5. So if we sketch this graph, or right around x equals -3. So here would be -3. And this function right at -3 has a hole. 1, 2, 3, 4, 5. Not a hole, but it has a dot right there at 5, because when we are at exactly x equals -3, the function value is 5. However, we have a hole at -3 of x squared minus 9 over x plus 3. And that hole is located at, as I said, -3, which would also be at -6. So there is a hole down here at -3, -6. 1, 2, 3, 4, 5, 6. And this function would be coming through like this. So you can see that this definitely is not continuous, but we have now kind of formalized the procedure where we can check the function to see if it exists, see if the limit exists, and then determine whether those two are the same if they exist. If they're not the same, the limit doesn't exist. So you can see too that if this problem was changed and this 5 was actually a -6, if we did that, then that basically would slide this point down here and fill in that removable discontinuity, and then it would be continuous. But for the fact that it wasn't -6, but that it was 5, not continuous. Next problem. These are pretty popular in terms of testing you on continuity on the AP exam. And this says, what would the value of k, what value of k would make f of x continuous at x equals 2? Well, let's go through the three-step process and see what we could use. Well, first of all, we're talking about at x equals 2. So does the function exist at 2? Yeah, f of 2 is going to be k times 2 minus 5. So we don't know what k is, but still, nonetheless, if I were checking this for continuity, that would have to be, there would have to be a value for that f of 2 is equal to k times 2 minus 5. Now, the second thing would have to be that the limit as x approaches 2 must exist. And, you know, the thing about the limit existing, if the limit exists, to check that, what has to happen is that the left-hand limit of that function at 2, it has to be equal to the limit on the right-hand side. And that gives me an equation that I could use to actually solve for k. So let's try that and see. So if I were to look at what would be how could I evaluate the limit just to the left of 2? Well, just to the left of 2 would be this 3 minus x squared. So I'm going to evaluate that through direct substitution. That's going to be 3 minus 2 squared. And that would have to be equal to the right-hand limit at 2, which would be this function with 2 directly substituted in. So that would be equals 2k minus 5. So that is an equation right there that I can solve for k. So let's do that. So this is 3 minus 4 is equal to 2k minus 5. That's a -1. I add 5. It looks like I'm going to get 4 equals 2k. So therefore, if k is equal to 2, then it's going to make my right hand and left hand limit the same. Now, let's just do a quick check on that for a second, class. Let's check it. Right, so if k is 2, so that would make this 2x minus 5. And if we go through the three-step check, number 1, does the function exist? Yes. It would be at 2, it would be f of 2 is equal to a -1. Now, that's one check there. Now, does the limit as we approach 2 exist? Well, if it's a piecewise function, I got to check both the left hand and right hand. So if we check the left hand, which would be this one, when x is 2, I get 3 minus 2 squared, or 4, which is a -1. There you go. And if I check it from the right hand, it would be 2 times 2 minus 5, which is also -1. So yeah, the limit exists, and it's a -1. Those two happen to be the same. So the function limit, or the function value at 2, is equal to the limit as we approach 2. So therefore, we have shown that k being 2 does make that function continuous at x equals 2. The next question is, what's the ordered pair transition point where the 2 points meet? Well, That's going to be obviously at an x value of 2. And we already saw that when we evaluate our function at 2, it's a negative 1. So that's the transition point where these two functions, when k is 2, they're going to come together and meet at the y value of negative 1, making the function continuous. And then part C, show that f of x is continuous at x equals 2 using the definition of continuity. I really already did that up here. This was my verification that k being 2 actually did meet step 1, step 2, step 3 of that definition of continuity. All right, I want to talk a little bit about properties of continuity. Before I do that, though, be sure if you are watching this live or if you're watching it on replay to hit the like button to let me know that you were here. Put your name down in the comment section. That'd be helpful. Also, let me know where you're watching it from. And be sure to subscribe so you get notified when I'm about to go live. All right, so let's go back to properties of continuity. So what I've shown you up here in this example and in the definition of continuity using limits is that we can check for continuity at a particular point. Now, but we can also discuss continuity in terms of intervals over which a function is continuous. So these are some properties. Let's take a look at this. So if I have functions f and g that are continuous at a particular point, then also the following functions would be continuous at that x value. So if I take my function f and it's continuous at x equals c and I multiply it by a constant, then it's still going to be continuous at that value. If I do sums and differences of continuous functions, that result will be continuous. Products of continuous functions are continuous, and same with quotients, so long as at the value c, we're considering that the denominator function is not equal to 0. And it also works with compositions of functions. So let's take a look at a slightly different question than we just worked. And that is, here is a piecewise function h of x. And it says, for what values of x is h of x not continuous? Now, I know that I have to check for sure at x equals negative 2, because that's where these functions are going to come together and meet. And I need to make sure that they meet at that same y value and that the function exists at that x value of negative 2. So I'm going to apply my 3-part check to x equals negative 2. But let's consider these other functions. Are there other places besides negative 2 where I might see discontinuities? Well, this function right here is a linear function, and which I could classify it as a polynomial, just as x cubed minus 6x plus 3, also a polynomial. One thing we know about polynomials is they are continuous over all real numbers. So there is nothing to worry about in terms of there being any other discontinuities here or here besides negative 2 for those functions, because there could be no other discontinuities. The function 3 is a horizontal line, so there's no discontinuities there. So I can say that that h of x is continuous at all values of x except possibly for x equals negative 2. But I'm going to check that, right? So that's my task right now, is to go to see, hey, is this thing discontinuous at negative 2? So let's start down the process. Let's find h of negative 2. Well, h of negative 2 is a 3. Because when x is exactly negative 2, my y value for the function is 3. Number 2, I need to see if the limit of h of x as we approach -2 exists. Now, so that's the question. Does it exist? For it to exist, the left hand and right hand limits have to be the same. So we'll check the left hand limit. So let's take the limit of h of x as x approaches -2 from the right. Let's do the right hand limit. From the right of -2 would be this function. And I'm going to do that with direct substitution. So that would be a -2 to the third power minus 6 times -2 plus 3. That's going to be a -8 plus 12 plus 3. I'm looking at a value of 7. I'm now going to evaluate the left-hand limit at -2. So the limit of my function as x approaches -2 from the left. -2 from the left, I'll be evaluating -2x minus 5. So -2 times -2 minus 5. So that's -4 minus 5, that's -9. So it looks like at -2, -8, -12, yes. So at there is a discontinuity then, because the limit does not exist, because the left hand and right hand limits are not the same. So we can say that h of x is not continuous at x equals -2, and I'll give a because statement, right? Because the limit of my function h of x as x approaches -2 equals a DNE, does not exist. Let's move on. All right, here is another piecewise function, and here what we've got, which is a favorite of College Board, is they give you a system of equations here, which happens to be in the form of a piecewise function, but I've got unknown constants, right? That is what the College Board loves to do. You've seen it on the SAT. Find the constants to make something true. Here it says use the 3-part definition of continuity to create a system of equations, then find the values of a and b so that f of x is continuous for all real numbers. Okay, so it looks like this is a quadratic, that is a constant, that is a linear function. So all 3 of those would be continuous over all real numbers. So the only place really that we have to check is at x equals -1. So here's what we're going to do. I'm going to start going down the 3-part process here. So f of -1. So I'm going to state this, right? F of x is continuous. So we'll say that f of x is continuous for all x, except possibly x equals -1. So we will check for continuity. So we'll check for continuity at that one location. The first step to checking for the continuity is say, okay, what's f of -1? What is my function when exactly x is equal to -1? Well, according to the piecewise function, it's equal to 6. Now, what I'm going to do is I'm going to say that, well, what has to happen here is that the left-hand limit as x approaches -1 of f of x, well, let's just state it this way, that it must exist. Okay, well, for it to exist on a piecewise function, then the left-hand limit and the right-hand limit have to be the same. So what we could say then is that we have this equation. The limit as x approaches -1 from the right must equal the limit as x approaches -1 from the left. That has to be true for the limit to exist, which is what we want. We want it to exist, and we want to find A and B that will make it so. All right, so that's the idea. So from the right, then we would be using this. It would be ax squared plus b. But remember, I'm going to evaluate this by direct substitution. So I identified that this is the portion of the piecewise function that comes into play when I am to the right of -1. So really what I'm going to do here is I'm going to say that this is a times -1 squared plus b. And over on this side, to the left of -1 would be this one. Evaluating that also by direct substitution, where -1 would be put in for x, I get 2a times -1, and that would be minus b. Okay, so all I did was evaluate the left-hand and right-hand limit by direct substitution and set them equal to each other, because for the limit, for the function rather to be continuous at -1, the right and left-hand limits have to be the same value. So that if I simplify this equation, I get a plus b is equal to -2a minus b. But I need another equation, because what I have right there is I have a system of equations with two variables. So I want to get myself one more equation. Okay, and so let's see how we're going to do that. So what do I want to do here? So what can we do? Well, what has to be true, right? The third condition. So this was our first condition, our second condition. Our third condition is that these things have to be the same, okay? So that means I could take the left-hand limit, a plus b, right? I'll write it this way. F of -1 has to equal to the limit as x approaches -1 of f of x. Okay, well, I know what f of -1 is. It's 6. Now, the limit is going to be equal to either of these two things. So I'm just going to say that it's equal to a plus b. I could have put -2a minus b. That'd be fine as well, because I've already equated those two things together. So here is our equation. So what I've got here is I've got a plus b equals -2a minus b, and I have 6, or I have a plus b is equal to 6, like that. Okay, so what do we want to do? I would like to solve this system of equations that I have, and that's exactly what I'm going to do. So the first thing I'm going to do is I can set both of these things equal to 6, right? I can say that a plus b is 6. I can say that -2a minus b has to also be equal to 6, just through substitution. If I add those two equations together, b's cancel. This is a -a, and I get a is equal to -12. Then I can back substitute and figure out then what b has to be. So now that I know that a is -12, I can say that -12 by substituting this back in to this equation, -12 plus b is equal to 6, and so b has to be equal to 18. So if a is equal to a -12 and b is equal to 18, I have just determined that those two constant values, when put back into this function, is going to make the function continuous. So just to kind of recap this problem, we first identified that all three of these were continuous everywhere because of the nature of their functions. They are all polynomials. And this one's a linear, that one's a constant, that one's a quadratic. So the only possible discontinuity would be when x is equal to -1. So we started off in saying, well, what is f of -1? It is 6. Then we said that the next condition that has to be met is that the left-hand and right-hand limit have to be the same, so we equated those. Through direct substitution, we evaluated the right-hand limit and the left-hand limit at -1. That gave us this equation right here. But we also knew that the third condition was that f of -1 had to equal to the limit. So I could set each one of those equations equal to 6, forming a system of equations. And that allowed me to very easily solve that system of linear equations to get A and B. All right, now so we're at about 9:10, so I've got some time, and I want to go into the intermediate value theorem. So this is really kind of like the very first theorem that we present in AP Calculus, and it's a pretty easy one. It's easy to make sense of, anyways, because it is logical. And here's what it is. I call it the in-between value theorem, because when we say intermediate value, I'm talking about in-between values. I'll show you what I mean. So in a broad sense, we could state the intermediate value theorem like this. A function that's continuous over a closed interval cannot skip values. Now, when I say cannot skip values, I'm talking about y values. Like, because the values of a function are the y values, right? The x's are the locations where the function may exist, and then the y values are the values of the function. So here's what I mean. So suppose that I have a function f of x, and I pick a value on the x-axis that I call a, and another one that I call b. Well, this y value here, we could label this as f of a. And we come up here, we hit the function, and we come over, and that is f of b. Now you can see that this function is continuous over the closed interval, okay, between a and b. So it's continuous at a, it's continuous at b, and at every point in between. So what the intermediate value theorem says that if the function is continuous over the interval a to b, and then we come along and we pick a value on the y-axis that happens to be in between, I'll call it L, that's in between f of a and f of b, that means there must exist at least one value that's associated with L that would fall in between a and b, and I'll call that c. So if the function is continuous, and I give you over an interval, and I give you a value on my y that falls between the corresponding y values for a and b, then that means there has to be at least one value of x that falls in between the x values of a and b. All right. So in other words, I know that if the function is continuous, that between a and b, there's going to exist a y value for every single y value between here. Right? So it can't skip values. So when you look at all of the numbers between f of a and f of b, they're all covered, right, by the values that go in here. And notice, in this case, there's only one value that goes with this L. The theorem says there has to be at least one. There could be more than one because the function may have several relative extrema, and you could come across at that value of L and hit several x values, but you got to hit at least one. Okay, so that is the intermediate value theorem. Now, so stated more formally, okay, this would be the theorem if we want to be a little bit more precise. If a function is continuous over a closed interval from a to b, then f of x will take on every value between f of a and f of b. So this goes right along with the graph that I was just showing you that I made up, that it's continuous between a and b. We can see that for every x value between a and b, including a and b, then that means that f of x will take on every value between f of a and f of b. Now, these are the three conditions to use the intermediate value theorem. We have to know that f of x is continuous over the interval that we're considering. So we're given a value of x's, and we need to first confirm that it's continuous over the interval. F of a cannot be equal to f of b. And then f of c must be between f of a and f of b. So whatever, in other words, whatever y value that we choose, it has to fall somewhere between the corresponding y values for a and b. All right, so let's see how we might use this. I think this will probably be our last problem for tonight. So here's the example. Use the intermediate value theorem to show that f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. Okay, so has an x crossing, right? That's what we mean by having a 0. Okay, so this is one of the great uses for the intermediate value theorem, because we use this to show whether that function right there crosses the x-axis somewhere between 0 and 1. So here's what we do. Here's our interval. First of all, is this function continuous? Yes, f of x is continuous over interval 0 to 1. I'm not going to state why it is. It's self-evident, right? This is a polynomial, and all polynomials are continuous over all real numbers, and their domain is all real numbers. So that's the first condition. Now, the next thing that I have to do is I have to evaluate the function at at x equals 0 and x equals 1. So let's do that. So f of 0 is equal to a negative 1. F of 1 is equal to 1 cubed plus 2 times 1 minus 1. I'm going with a value of 2. Now, I'm going to sketch the scenario here. This is what's happening. At x equals 0, this function is at negative 1. Out here at x equals 1, it has a y value of 2. And this function's continuous, all right? I know that it's continuous because I know properties of polynomials. So this function, whatever it's doing, it's coming, I don't know exactly what it's doing, but it's got to be doing something like that because it's continuous. So it has to span all of the y values between negative 1 and 2 as it's traveling from 0 to 1. So of course, it stands to reason it has to cross the x-axis somewhere, right there between 0 and 1. So what I'm going to do is I'm going to write that out kind of as an answer to this, right? So I want to kind of formally present this as an answer. So let me show you what I want to do here. Okay. So what I can say here is because 0 is greater than f of negative 1 and f of 0. So the value, since we're looking for a 0 here, I'm talking about when f of x is equal to 0. So that number right here, 0, is this number here. It's greater than f of negative 1 and less than f of 0. So it's sandwiched in between. So going back, all I'm trying to say is that this number that I'm interested in is sandwiched between those two numbers. That's what my statement is saying right here. So I'm going to say because f of negative 1 is less than 0, less than f of 0, or I should say, f of 1, sorry, in between, because this is f of 0, this 2 up here is f of, that's f of 1, sorry, class. And this is f of 0, my bad, right there. I'm talking about the interval from 0 to 1. F of 0, which was the negative 1, right? And f of 1, which was the 2, and 0 is in between those values. And because my function f of x is continuous over that interval, closed interval from 0 to 1, then there must exist at least one value of c such that, oh, and I'm gonna be a little more specific. There must exist one value of c between my values here, right? Between 0 and 1, such that the function evaluated at that c is equal to 0, making it an x-intercept. Now, it didn't ask me to do this, but oftentimes on a problem like this, they'll ask you to go ahead and find that value of c, which means in this case, I would have to set the function equal to 0 and then solve for x. Okay, or if it was, if it was checking to see whether this function had a value of 4 on the interval, then you would then actually plug in c for x and then set it equal to whatever that value is. So if I were to solve this, I would have to then solve the equation c cubed plus 2c minus 1 equals 0, and find out what the real solution is to that. If there's more than one that happens to fall between 0 and 1, then that would be my c value. Now, oftentimes when you are finding the c value, there may be more than one solution to the equation that you set up, but of course we're only interested in any solutions that would fall between 0 and 1. But without having to look for it, I don't really need to find it to know that it's there because of the intermediate value theorem. Because if f of 0 is -1 and f of 1 is 2, somewhere between 0 and 1, this function had to have crossed the x-axis. All right, class. So that's going to be it for tonight. We got in under 1 hour. And again, if you stayed here all the way to the end, be sure to like and subscribe, and let me know where you were watching from in the comments section. I would greatly appreciate it. Now, next week, what we're going to be doing is I'm going to be doing a complete review of limits. So I'll probably be doing a practice test on limits. So you want to tune in for that. My class will be having their first exam on limits the week after that, during the school week after next Sunday. So they'll definitely want to watch that one, because I'm going to cover all of the concepts and do lots and lots of practice problems. If you join in live next week and you've got questions that you'd like me to go over, I'd be happy to do that too. And you can email them to me at the email address that is posted down there in the banner, and I'd be happy to work those problems for you. Okay, very good. Hope you all have a great week at school. Thanks for tuning in, and I'll see you next Sunday.